Machine learning architecture. This is an architectural diagram of machine learning. Machine learning in artificial intelligence, a subject within computer science, discipline concerned with the implementation of computer software that can learn autonomously. Now we are focusing on data in real-time processes. Data is ingested from different sources from real-time systems like IoTs, CCTV cameras, streaming media data and transaction logs. As an example, we can consider streaming media data. Now we are focusing on data from batch processes. Data that is ingested can also be data from batch processes or non-interactive processes like Linux cron jobs, Windows scheduler jobs, and so on. As an example, we can consider Linux cron jobs. The cron command line utility, also known as cron job, is a job scheduler on Linux-like operating systems. Users who set up and maintain software environments use cron to schedule jobs, commands or shell scripts to run periodically at fixed times, dates or intervals. It typically automates system maintenance or administration, though its general purpose nature makes it useful for things like downloading files from the internet and downloading emails at regular intervals. Now we are focusing on data store. The raw or aggregated data from data collectors is stored in data stores like SQL databases, NoSQL databases, data warehouses, and distributed systems like HDFS. This data may require some cleaning and preparation if it is unstructured. The file format in which the data is received varies from database dumps, JSON files, Parquet files, AVRO files, and even flat files. For distributed data storage system, the data upon ingestion gets distributed to different file formats. As an example, we can consider RDBMS, Relational Database Management Systems. RDBMS are legacy storage options and are extremely popular in the data warehouse world. They store data retaining the atomicity, consistency, isolation, and durability, acid properties. However, they suffer from downsides, storage in volume and velocity. As another example, we can consider MongoDB. MongoDB is a popular NoSQL document-oriented database. It has a wide adoption in the cloud computing world. It can handle data in any format like structured, semi-structured, and unstructured. With a high code push frequency, it is extremely agile and flexible. MongoDB is inexpensive compared with other monolithic data storage options. As another example, we can consider Bigtable. This is a scalable NoSQL database from Google. Bigtable is a part of the reliable Google Cloud Platform, GCP. It is seamlessly scalable with a very high throughput. Being a part of GCP enables it to be easily plugged in behind visualization apps like Firebase. This is extremely popular among app makers who use it to gather data insights. It is also used for business analytics. As another example, we can consider AWS Cloud Storage Services. Amazon AWS is a range of cloud storage services for IoT devices, distributed data storage platforms, and databases. AWS data storage services are extremely secure for any cloud computing components. Now we are focusing on machine learning engine. Here we consider data transformation, feature generation, model output, performance tuning, and model engine. As an example, we can consider Google Cloud ML engine. The Google Cloud ML engine is a hosted platform to run machine learning training jobs and predictions at scale. The service treats these two processes, training and predictions, independently. It is possible to use Google Cloud ML engine just to train a complex model by leveraging the GPU and TPU infrastructure. The outcome from this step, a fully trained machine learning model, can be hosted in other environments including on-prem infrastructure and public cloud. The service can also be used to deploy a model that is trained in external environments. Cloud ML engine automates all resource provisioning and monitoring for running the jobs. It can also manage the life cycle of deployed models and their versions. Now we are focusing on data transformation. Data transformation is the process in which you take data from its raw, siloed and normalized source state and transform it into data that's joined together, dimensionally modeled, denormalized and ready for analysis. Without the right technology stack in place, data transformation can be time-consuming, expensive and tedious. Nevertheless, transforming your data will ensure maximum data quality, which is imperative to gaining accurate analysis, leading to valuable insight that will eventually empower data-driven decisions. As an example, we can consider this code segment. This code is in Python. Here, importing quantile transformer scalar from scalar and preprocessing. In this code for the model creation, and this is fitting and transforming the model on A-train inputs. With related to quantile transformer, that transforms features using quantiles information. This method transforms the features to follow a uniform or normal distribution. Therefore, for a given feature, this transformation tends to spread out the most frequent values. It also reduces the impact of marginal outliers. This is therefore a robust preprocessing scheme. Now we are focusing on feature generation. Feature generation is the process where data is analyzed and We look for patterns and attributes that may influence model results. Features are usually mutually independent and are generated from either raw data or aggregated data. The primary goal of feature generation is performing dimensionality reduction and improved performance. Here you can see ML feature engineering architectural view of Netflix feature store. The feature store developed by Netflix supports both online and offline model training and development. Online microservices enables the framework to collect the data elements required by feature encoders in a model. It further passes the this downstreaming for future use by offline predictions. The fact logging service of Netflix logs user-related, video-related, and computation-specific features in a serialized format in appropriate storage units S3. The unique point of this architecture is the presence of components that help to create context to snapshot data of various microservices for selected context, build API to serve this data for a given time coordinate in the past. As snapshotting data for all context, example, all member profiles, devices, times of day, would incur overhead and cost. Netflix relies on selecting samples of context to snapshot periodically at a regular intervals twice daily, though different algorithms. It achieves this through Spark, by training data on different distributions and by using stratified samples based on properties such as weaving patterns, devices, time spent on services, region, etc. Netflix embraces a fine-grained service oriented architecture for cloud-based deployment model. Here you can see online system and offline experiment. In microservices, you get facts from facts to online feature generation. These features are moved to shared feature encoders and also move to online scoring. Then it can move back to features. Then it will go to offline feature generation. Then it can move to shared feature encoders and also can move to model training, and it will go to online scoring again with deployment models. Then it came out here. As an example, you can consider this Python code here. You can define your features in a way that is more explicit and less tied to the specific of the raw data in original data frame. The resulting value is an RDD of word sequence feature. Here you can see the code, Python code. Here define the base, trait, fall types of features, and here require the feature types to have names here, and the type parameter hold the type of values generated by feature. Here defines the base, trait, fall features as an extension of feature types here, and requires that the features have values of the type specified in the feature type. Here define a case class for features consisting word sequences. Here specified that the type of features being generated is a sequence of strings words. Here select the words column from the data frame. Here maps over rows and applies function to each. And here creates an instance of word sequence feature named words. Here gets extracted words out of a row. And here prints features for inspection. Now we are focusing on model output. The model output is correct, useful for decision making at some degree of probability. Models are not 100% correct, but are rather best guesses given the amount of data the model has seen. The more data in the model has seen, the more likely it is to give useful output. Here you can see machine learning before training. In a machine learning problem, the model is unknown initially. We have no way of determining the output value based on the input values. If we have a set of data where inputs and corresponding outputs are known, we can use supervised learning to train the machine learning model. Supervised learning means we keep track of how well the machine learning model is predicting versus the known outputs. Each iteration of the learning process refine the model to improve the prediction. Here you can see input which is known is moving to the model which is unknown. And model is connected to the output which is known. This is machine learning after training. After the machine learning model is trained, we now have a model to determine output, but there is some level of uncertainty in the predicted output. This uncertainty arises from the model. In prediction mode, we still have known inputs that are fed into the model. Here you can see the inputs which are known are moving to model which is learned, and the model is provides output which are predicted. Here we can consider this Python code segment as an example. The idiom for defining a model in PyTorch involves defining a class that extends the module class. The constructor of your class define the layers of the model, and forward function is the override that define how to forward propagate input through the defined layers of the model. Many layers are available, such as linear for fully connected layers, CONV 2D for convolutional layers, and maxpool 2D for pooling layers. Here this is an example with simple MLP model with one layer. The activation functions can also be defined as layers such as ReLU, softmax, and sigmoid. The weights of a given layer can also be initialized after the layer is defined in the constructor. Now we are focusing on performance tuning. Performance tuning and error detection are the most important iterations for a machine learning system, as it helps to improve performance of the system. Machine learning systems are considered to have optimal performance if the generalized function of the algorithm gives a low generalization error with a high probability. This is conventionally known as the probability approximately correct PAC theory. Here you can see fine-tuning machine learning model hyperparameters. Here training data of independent variables, also known as features. Test data of independent variables. Ytrain, training data of dependent variable. Ytest, test data of dependent variable. For instance, if you are forecasting the volume of waterfall based on the temperature and humidity, then the volume of water is represented as Y dependent variable, and the temperature and humidity is are the X independent variables or features. Training data of X is then known as Xtrain, which you can use to train your model. Hyperparameters are parameters of the model that can be input as arguments to the models. It is often easier to improve the data that we feed into the models than to fine-tune parameters of the model. If you want to improve accuracy of your forecasting model, then please enrich data in the feature set first. If you feed poor quality data in, then the model will yield poor results. The most important prerequisite is to decide on the metric that you are going to use to score the accuracy of uh, forecasting model. It could be R squared, uh, adjusted R squared, confusion matrix, F1, recall, variance, etc. Once you have prepared your training set, enrich its features and scale the data, decompose the feature set, decided on scoring matrix, and train your model on the training data. You should test the accuracy of the model on unseen data. The unseen data is known as test data. You can utilize cross-validation to access how your model works on unseen data. This is known as generalization error of your model. Cross-validation. There are two common cross-validation methodologies. Holdout cross-validation. It is the most wise machine learning practice to train your model and score its accuracy on same data set. It's far superior technique to test your model with varying model parameter values on an unseen test set. It is a good practice to divide your data set into three parts: training set, validation test set, and test set. Train your model on the training set 60% of the data, then perform model selection tuning parameters on validation set 20% of the data, and once you are ready, test your model on the test set 20% of the data. Create your training, validation, and test data sets proportions according to the needs of your machine learning model and availability of data. K-fold validation. K-fold cross-validation is a superior mechanism than using holdout cross-validation. The way it works is that the data is divided into K-folds parts. K1 folds are used to train the model, and the last fold is used to test the model. The mechanism is then repeat K times. Furthermore, each time the number of performance matrices can be used to access the score and score the performance. The average of the performance metrics are then reported. The class proportions are preserved in state field K-fold. Once accurate forecasting scores have been established, find out all the parameters that your model required. You can then use validation curves to explore how their values can improve the accuracy of forecasting models. Before we tune the parameters, we need to diagnose and find if the model is suffering from under or overfitting. Models that have a large number of parameters tend to overfit. We can use validation curves to resolve this issue of overfitting and underfitting in machine learning. Parameters are also known as hyperparameters. Validation curve is utilized to pass in a range of values for model parameters. It changes the values of the model parameters one at a time, and then the accuracy values can be plotted against the model parameter value to access the accuracy of the model. For example, if your model takes a parameter named number of trees, then you can test your model by passing in 10 different values of the parameter. You can use validation curve to report accuracy on each parameter value to access the accuracy. Finally, take the score that returns highest accuracy and gives you your required results within acceptable times. Once we have retrieved the optimum values of individual model parameters, then we can use grid search to obtain a combination of hyperparameter values of a model that can give us the highest accuracy. Grid search evaluates all possible combination of the parameter values. Grid search is exhaustive and uses brute force to evaluate the most accurate values. Therefore, it is computationally intensive task. The key here is to always enhance the training set as soon as more data is available. Always test your forecasting model on richer test data that the model has not seen before. Always ensure that the right model and parameter values are chosen for the job. It is important to feed more data as soon as it is available and test accuracy of the model on continuous basis so that the performance and accuracy can be further optimized. Here you can see a control system pipeline is connected to machine learning model in which there are parameters, and this model is connected to a scoring system. Here we can consider this Python example here. For example, if your model takes a parameter named number of trees, then you can test your model by passing 10 different values on the of the parameter. You can use validation curve to report accuracy of each of the parameter value to access the accuracy. Finally, take the score that returns highest accuracy and gives you a required result within acceptable times. Once we have retrieved optimum values of the individual model parameters, then we can use git search to obtain a combination of hyperparameter values of model that can give us highest accuracy. Git search evaluate all possible combinations of the parameter values. Git search is exhaustive and uses brute force to evaluate most accurate values. Therefore, it is computationally intensive task. Here you can see git search CV of HCI kit learn to perform git search. As an example, we can consider mean squared error. Imagine for a regression problem we have the line of best fit and we want to measure the distance of each point from the regression line. Mean squared error MSE is the statistical measure that would compute these deviations. MSE computes errors by finding the mean of the squares of each such deviations. This shows the diagram of MSE. As an error example 2, the mean absolute error MEA is another statistical method that helps to measure the distance error between two continuous variables. The continuous variable can be defined as a variable that could have an infinite number of changing values. Though MEEs are difficult to compute, they are considered as a better performing than MSE because they are independent of the score function that has a large influence on the errors. Here you can see the MAE in action. Now we are focusing on model engine. A machine learning model engine is responsible for managing the end-to-end flows involved in making the machine learning framework operational. The process includes data preparation, feature generation, training and testing a model. Here you can see a pattern recognition engine. In general, correlation patterns are managed by administrators and the Big Panda customer success team. The machine learning engine is able to supplement the human design patterns by autonomously searching for new correlations and suggesting new patterns. Here we are basically consider about Big Panda. Here Big Panda's machine learning engine will automatically generate correlation patterns suggestions based on the historical user data. Upon the integration of monitoring tool, the review process begins and automatically generated patterns will be suggested in the correlation pattern settings page in a few days. The rate at which the first pattern is generated is dependent upon the richness and size of the available data. Over time, as more data flows through the system, additional patterns will be recommended at an increased and variable rate. Once the machine learning engine suggests a pattern, administrator can decide to activate it, reject it or customize it within the editor. The real-time preview of the pattern editor gives you instant visibility on the impact a suggested pattern would have on correlated alerts in your system. Suggested correlation patterns are made to stand on their own, but new patterns can also be modified to complement an existing set of in-use patterns. The end result is better correlation reach with higher quality incidents to help your team resolve issues faster. Here you can see monitoring events are moving to connected to pattern recognition, and pattern recognition is connected with machine learning pattern recognition and user control pattern management, and pattern recognition is moving to correlated incident. This is the end of my presentation. Thank you very much for watching.